take the again the formation of swept wing. Swept wing, but we'll put cardwise. So in this, the model we take is as usual the same thing. And this is the elastic axis, and you have your aerodynamic center and mass center. And this is your theta bar, okay, and this is my y bar. Of course, this is my y axis, x axis, this is my wind direction, and this is the effective route. The same way you draw a effective tip, okay, and you take now cardwise segment, and the card you call this as C bar, and this distance you call it E bar, and this distance you call it D bar, okay. And of course this is the sweep angle to the elastic axis. Now essentially what we are going to do is we resolve our oncoming velocity into two components. Okay. This is u and this is lambda, so u cos lambda, and this is u sine lambda. So the oncoming flow normal to the leading edge, I take it as u cos alpha, and now I get my distributed lift. Distributed force is basically C bar and CL bar Q, and I will have actually Q is half rho U square, so I will have Q cosine square lambda minus bar G and load factor N. Okay, M bar is mass per unit length along again Y bar. Similarly, you will have your distributed twisting moment, distributed torque, I call it T bar Y bar. This is C bar CL bar Q cosine square lambda into E bar, because E bar is the offset between aerodynamic center and elastic axis, and then plus C bar square Q cosine square lambda C bar MAC. This is the aerodynamic moment coefficient. Then minus N M bar G D bar. Okay. So this is my twisting moment. Now you can go and write, but please understand all this. All are along cardwise direction. Okay. Now your bending equation is essentially d square by d y bar square EI d square w by d y bar square equals your distributed load. Distributed load is here. You will have C bar CL bar Q cosine square lambda minus N M bar. And similarly your torsion equation becomes d by d bar of Gj d theta bar by dy bar. This is equal to negative of the twisting moment. So you will have minus C bar CL bar Q cosine square lambda into E bar minus C bar square Q cosine square lambda C bar MAC plus N M bar G D bar. Okay. Now this is my torsion equation. Now what you do is, as usual, you split your CL bar as CL bar rigid plus CL bar elastic. Okay. And then collect the terms of the elastic to the left side and then write your complete equation. Okay. Now before we shift it and write, what is CL? This is nothing but lift coefficient, okay, of the cardwise. But lift coefficient becomes essentially CL bar E is some CL alpha into angle of attack. What is the angle of attack? Okay, this is the question which we have to be careful here. One part of the angle of attack is theta bar. Theta bar is basically twist. So you will write one part is theta bar. Then there is one more component which you have to take because of bending deformation. How that comes about is u sine lambda is going along the y bar, right? Now when this beam is bending, u sine lambda will be like this. It is like if I take the slope, this is my wing, u sine lambda will be like this. Okay, and the normal component, this is the slope, this is slope of the deformation in bending. Now you can have a normal component. Okay. The normal component will be u sine lambda times that, because sine of that slope is very small. You take the normal component, you will have something like this. This is u cosine lambda. The normal component will be okay. Now this is a change in angle of attack at that section. But please understand, this is a little tricky. In the sense, this section which was originally like this, it has become like this. And you have a velocity component which is coming. A normal component you take. The normal component is u sine lambda dw by dy. The oncoming velocity is cosine lambda. So you divide by that, this angle will be basically tan lambda dw by dy bar, and this will reduce the angle of attack because it is coming down. So you will have here tan okay. So you see CLE as this form. Okay. So technically, if I take this term, split it, CLR, so that is the rigid angle of attack. That will stay on the right hand side. Left hand side, that CL bar E will go left hand side. And that CL bar E will go in both the terms. Then you have to substitute for that CL alpha, which is the aerofoil lift curve slope, but the angle of attack is theta bar, which is due to twist. This is due to bending. Okay. This is how in chord-wise rigid formulation the coupling between bending and torsion happens. Okay. So this is this form is different from stream-wise rigid formulation. Okay.
In this also CL alpha would be for the stream.
CL alpha is
no, we have that CL alpha.
No, CL alpha here is directly the aerofoil because this is the aerofoil. See, this is different. This CL alpha is directly CL alpha of the, because the flow is normal to the leading edge, whereas in the other case flow is not normal to the leading edge. That is why there CL alpha lambda not equal to 0. Okay. Whereas here it is directly the CL alpha. Okay. Now this is how the coupling. Of course, the boundary conditions you have. I'll just mention it so that you have these boundary conditions. BCs will be W0 is 0 and dW over dy bar at 0 is 0. That is the slope is 0. Then theta bar 0 is 0. And then Gj d theta bar by dy bar at L is 0, and then you will have other two, EI d square W by d y bar square is 0 at L, and d by dy bar of EI dW by at L is 0. So these are your boundary conditions. Okay. Because this is the free end. Shear is 0, bending moment is 0. Now you see, you can solve this problem again with the boundary conditions and then apply Galerkin method. Okay, but please understand this formulation looks different from stream-wise formulation, rigid formulation. Okay. Now the question is, you may say which is right, which is wrong, because you look at the construction and then solve. So these are all beam bending torsion type of a problem. Okay, we are not taking this as a plate. This is a large aspect ratio beam. Therefore, we will calculate by both the methods. So the assignment I will send you. You calculate the divergence speed for the wing by both approaches. Okay, and then compare the results, how they vary. Okay, so now we will do one example problem of how to apply Galerkin method for getting the divergence of a wing. But for this I take the problem which I gave you in the earlier. So I erase this entire thing because I thought this will be good to have, how to have the solve a divergence problem. Okay. Now we will take this same. You have a straight wing. This is an example. And this is the aerodynamic center, and this is the elastic axis, and the card is C. It's a straight wing, and we put at a particular point L/4 I have a spring. This offset I call it as EL, and this offset is E. Okay, and this is my x-axis. Now first we formulate the equation for this, which you already got the equation, but I thought if you have this EL, okay, this we are formulating for basically divergence. Okay, so the gravity will only be on the right hand side. Okay, it will not come on the left hand side, the weight effect. Okay, therefore we will apply the simple virtual work principle and then try to get the equation for this. You can apply Rayleigh-Ritz also. Please understand, for this problem you can apply Rayleigh-Ritz also, but I am solving by Galerkin for change. The strain energy expression will be U. Please understand, you have to write now the strain energy expression for the twist, which is because this is the twist theta, which is a function of okay, this is y I have used, so let me use y only. Okay, let me use y. Okay, it doesn't matter. X, y and z. Okay, so this is my x-axis. Theta is a function of, but plus I have a linear spring attached to the wing, which is like what this representation really means is I can have a wing like this and I can have some stiffener strut attached here. Okay, that strut is represented by a linear spring. Now the spring is going to deform depending on my twisting. The twisting will be because the wing twists, because this is a straight wing. Okay. Now what happens? This will be theta at L over 4 by the offset EL. That will be the deflection at this point. And then strain energy half K into the deflection square. So you will add the strain energy plus half K linear spring into EL theta at L over 4. Okay. Whereas this is an integral over 0 to L, that is a point function. Now I can modify this little bit because just for convenience I am writing it half 0 L Gj d theta by dy whole square dy plus this also I am writing it as K EL square theta square into delta y minus, I am using a delta function. Okay. Alright. That means if I use a delta function, that means this is 1 when y is L by 4, otherwise it is 0. Everywhere it is 0. So this is an easy way of representation. Now you can write what is del U. Variation in strain energy is, you will take the variation here. Okay, and then it will be integral, you will write what? Half will go off. So you will have integral 0 to L Gj del of and then dy plus integral 0 to L K E square theta delta theta your delta y minus over 4. Please understand this delta is a delta function.
EL, I think.
Okay. This is a delta function, this is the variation. Please understand. Both I, okay, slightly we ought to be clear. Now I can integrate this by parts. If I integrate it by parts, I will get Gj d theta over dy delta theta at 0 L minus integral 0 L delta theta dy plus this term will remain as it is. So you will have integral 0 to L K EL square theta delta y minus L4 delta theta dy. Okay. This is as far as the internal delta U. Now you have to write the external. Delta W external, but external For the present I am taking only the lift force. This is the virtual work external moment. Gravity I am leaving it because it is not necessary for you to have gravity. But if you want to take gravity, then you have to have that also, whatever moment. This will be delta W external, which you will have 0 to L, dynamic pressure card CL into E, offset, because that is the lift force into offset E, plus you will have dynamic pressure card square CMAC. And if you want weight, you can add that term here. That will be, then I have to define some center of mass line and with an offset some D. Then this will become minus, if the load factor is 1, mg into D. Into dy into, you have to be, sorry, before I go, let me write, this is the, what? No, I cannot write like this, wait a minute. This is external force, this is force into E into delta theta. This is directly delta theta. I'll have dy, okay. Whereas for the mass, I'll write minus mg, that distance is d, into, okay, because E into delta theta is the, if you take, this is the force is acting on this, which is normal. The virtual displacement at that point is theta into E, delta theta into E. Whereas the force acting on the center of mass line is down, the displacement that comes out is D into delta theta. And the minus sign because the force and the displacements are in opposite direction. Okay, now combine both of them, and you know that the boundary condition limit at the root is a fixed end, so delta theta is 0. At the free end, you say it is a free moment is 0. So this boundary condition will go up. In the sense d theta by dy. This is what will come out of the boundary condition, that theta at 0 is 0 and Gj d theta over dy at L is 0. This is the boundary condition. Now combining both, you will have, your equation will become minus, because you know that del u minus del w external is 0. You can write it in this fashion, or you take it, put it on that side, that is also fine. So if you write like this del u, you will have minus d over dy of Gj d theta over dy plus k E L square theta delta of y minus L over 4. I am going to keep delta theta term because every term has delta theta dy. This is a complete integral 0 to L. So finally we say delta thetas are arbitrary, therefore the integrand must be 0. That is what we are going to write. So this is my big expression. This will be minus. So you will have minus q c cl into E minus q c square cmac, then this will become plus mgd. This entire thing delta theta dy is 0. Okay. This is an integral 0 to L. So this is what your final principle of virtual or what you get. And this, now you say my delta thetas are arbitrary variation, therefore the integrand must be 0. And the integrand 0 gives you your equation of, basically in the divergence problem, the torsion deformation equation. Okay. So we will write that equation. That equation will be minus dy of g j d theta plus kl, not k e l square theta delta of y l minus 4. This you again, if you want, you can split it. CL rigid, CL elastic. So if you split CL rigid and elastic, you will have minus Q C CL elastic into E. And then rest of the terms I am shifting it to the right hand side. Okay. If I shift it to the right hand side, this will become Q C R into E plus okay, plus you will have this term Q C square CM AC, and this will be minus. Now you can write QL, sorry, CL E is CL alpha into theta, because for us that is the only deformation, there is no bending, this is a straight wing. You can substitute here, this part is stays as it is. So I am going to write here, I replace it CL alpha into theta into E. Okay, I have replaced it. The right hand side I am keeping it as it is. Okay, now you need to get your if I rearrange my equation once again, because this is for just convenience. Okay, I will have my equation like this. Because the minus sign I take it out. Gj d theta over dy minus k e l square delta y minus l by 4 into theta plus q c cl alpha into e theta equals, I will have it minus q c cl r e minus q c square cm ac plus mgd. With the boundary condition, theta 0 is 0, d theta over dy at L is 0, that is Gj. Okay. Now this is my entire torsion equation. You see, because this term, that spring is there, extra spring, that is a function of theta. So this will affect your divergence speed. Now here only how do I apply Galerkin? Okay. I gave a solution which is apply, you take the theta which is a function of y as some constant a1 into 2 y over L minus y over L whole square. This is assumed. Okay. That means you see this, when y is 0, theta is 0. When you differentiate d theta by dy, this will be 2 y over L, sorry 2 over L, and this will be 2 y over L square. So when y equal to L, this is also 0. That means this solution, it satisfies both the boundary conditions. Okay. Now what you have to do is, you have to substitute in the equation, and then because when you substitute, it will not satisfy the equation. You will have an error. That error, you call it as, error means everything. That is, this term, you again bring it to the left hand side, put the theta equal inside here, because this is independent of theta. Please understand. Only theta exists here. Then you will say it will not satisfy exactly. So you say, okay, my idea is to get basically A1. The Galerkin formulation tells you the error which is a function of y, because when I substitute here, this is going to be a function of y. All these things are functions of y. 0 to L, I call this function as phi1 y. Okay. So error is orthogonal to the assumed function. So I take this as okay. This is what I have to do. Now I am taking only one function here. If you take two functions, then you will get two equations. Okay. Error is same when you substitute both. Now what we will do is we will go back and calculate each function separately, because you have to understand that this is where we need a lot of integrals. Okay. Because the error becomes essentially, I can take it like this. This will be plus, plus, minus, equals some error which is a function of y. Okay. I have substituted here theta equals this function. Now this function will be sitting here, d by dy. Okay. What I have to do is I have to multiply phi1 into this. When I multiply phi1 into the entire term, the first term will be phi1 d by dy gj d phi1 by dy, because this is, you have to put them here. So I have to evaluate that integral. So what we will do is, we will write like this. Now let us make some assumption that it's a uniform wing. Uniform wing means Gj is constant and all the C, E, everything is constant. It doesn't vary along the span. So we call it uniform wing. Then what will be my, if I substitute error and the whole thing, because I am going to call this term, okay, this entire term, which is independent of theta, you can call it by some other name, so that it doesn't matter, you call it some F or Q or whatever it may be. Now phi1 you know, so first term I require integral 0 to L phi 1. Since I have uniform wing, you will have Gj d square okay. Please understand, the first term is going to be phi 1. You will have a1 will be there because a1 is what you substitute here. So you will have d over dy of Gj d phi 1 by dy. You follow? This is the first term. I am only taking Gj constant, so a1 is anyway constant. I am just evaluating this integral. This integral, you substitute this here and then evaluate the integral. Okay? When you evaluate the integral, you will get the, I will write the answer. This will become minus okay. If you evaluate this integral, then the second term, what it will happen? Second term is you will have minus again phi 1 k el square. You will get what? This is an integral. So you will put, because all this integral, the delta function will be there, delta y minus L by 4 into theta, right? This is what theta is, nothing but a phi 1, a1 phi 1 into, you will have that dy. So essentially this term will become integral 0 to L phi 1 okay, k el square delta of y minus L over 4 and a1 phi 1 dy, right? Now here you know that because this is a delta function, a1 is a constant, that okay, that I don't have to write it in this integral, okay, leave it, because a1 I am taking it everywhere, a1, that is a common constant, it will come out. So if I evaluate this integral, this is nothing but the value of the function phi 1 square at L by 4, okay. So I will get here, that is phi 1 square L by 4, that will become k el square. This will be 49 over 256. You can evaluate this integral. Okay, that means phi 1 square at L over 4. So you will get k el square 49 by 256. Then you go to the third term. Third term will be again, I erase this part, the boundary condition part. Third term will be plus, you will have again q, c, cl alpha, e, theta will be again a1, phi 1, you are multiplying by a phi 1 and you are integrating again dy, okay. And that integral, I will write it here. This is integral 0 to L q c cl alpha q c cl alpha e, and you will have phi 1 dy. a1 I am taking it as common because a1 is there everywhere. Here also a1. So that can be common term outside. Okay. Now if you evaluate this integral, this will be phi 1 square integral dy, that is actually 8 over 15 L. So I will write this Q C Cl alpha E, I think 8 over 15 L. That is this integral. Okay. And the other integral, this is independent of theta. So what I will have plus, this will be some integral P1 into the entire quantity, okay, into dy. Okay. This I can call it by some Q or whatever it may be. Okay. Therefore, now I am going to write my integral, the equation. After it will be A1 minus 4 over 3L Gj minus KL, not KL, KEL square 49 over 2 56 plus Q C Cl alpha times E 8 over 15 L. This is equal to sum Q1, that integral is this integral. Please understand. You can take it to the right hand side. With a minus sign will come, that is what I am writing it as Q1. Okay. Now, you see, this is nothing but this. So, you may say, what are my unknowns here? My unknowns are put A1, of course the rest of the quantity is Q. Now you see the problem becomes like this. If I am given the Q, that means I know the speed of the aircraft, that means I know the dynamic pressure, then what is my deflection? Because we assume that theta y is A1 into what? I think y over 2y over L, right? Minus whole square. And you know these quantities, the weight of the wing, and then this CMAC, whatever is the moment coefficient corresponding to that, CLR, you know that whatever initial angle of attack, alpha r. If they are all given, you know for every dynamic pressure, what is my A1, you can calculate. But suppose you are asked the divergent speed, then basically I don't know Q. You are looking for the value of Q, okay, for which this equation, in the sense basically you say if this term is 0, okay, then this is a finite quantity, Q1 is finite, equals one term which is 0 multiplied by another term, A1. That means you say 0 and infinity product is finite. That's what, but finite, what is the value, you don't bother. Therefore, the condition of divergence is, you say that setting this term equal to 0. That is a divergence. So now you know Galerkin method or Rayleigh-Ritz. Now they will all lead to an equation like this. Okay. Now if you say that, let me write the values here. So please understand what is the kind of problem we are solving. If we are solving divergent speed, you say this term is 0, because if this is 0 multiplied to a very large value, that means any value of very large value is a finite quantity. So you really don't have to evaluate this also. You are only setting this term equal to 0, so you will have Q C Cl alpha E 8 by 15 over L equals 4 over 3L Gj plus K EL square 49 over 256. This is Q, I am going to call it QD, because QD only this will be satisfied, not at every other Q. So you can find out, given the value of C, what are the values I specified, or I think I have given you the values. Let me write the values here. Gj is 2.5 into 10 to the power 7 Newton meter square, and the length is 15 meters, and chord 3 meters, and offset E is 0.5 meters, and EL is 0.25 meters, and the spring K is 10 to the power 8 Newton per meter, and CL alpha is 6.0, and density is 1.225 kg per meter cube. Okay. So I have given all the values. What you do is you go back, substitute. If you look at this entire expression, I am going to give you QD becomes, because this is 15, so it will become 5 over 2 Gj over E C CL alpha L square, okay, plus K EL square over E C CL alpha into L 49 over 256 multiplied by 15 over 8. Okay. This is the value which you have. Now if you substitute all those quantities, you can see the effect of this term and this term. If you substitute the values, I erase here. If you substitute, you simplify all the values, and I am just writing the final answer, which is 3.08642 10 to the power 4 plus 1.66151. Okay, because I am keeping both of them separately just to see the effect of that spring alone. Okay. Now QD is, you know that QD is half rho UD square. So substitute the value, you will get UD becomes essentially 278.5 meter per second with the spring, with K. Okay. Whereas without K, UD becomes actually 224.5 meter per second without K. Okay, that means I don't have this term. Okay, I am having only this term. Now you see, this is the difference is of the order of about 50 meter per second, which is about 24%, 20 plus percent. So the effect of spring at one location, you can increase your divergence speed substantially. Now the question is, this is with the approximate method using Galerkin, but the key step is I should choose the function which satisfies my boundary conditions. Okay, that is the essence. All the boundary conditions it must satisfy. Okay, and we have chosen only one function. Like that you can have several functions. Okay. Now this is where the entire problem is, what is the choice of the boundary function which satisfy my boundary conditions. Okay, in this problem. Okay. So that is why I have given you the boundary condition and you are able to evaluate all these things. If your function is not given, then you have to go and identify that function which satisfies that. So this is the problem in using Galerkin method. Please understand. But Galerkin method starts with the equation, the field equation and the boundary conditions. Field equation, when you substitute, it gives you an error. Error is multiplied by the assumed function. If you have a series of functions, each function you put it, you will have so many equations. Okay. Here I have used only one to get the solution. Now I say, okay, you are going to use this technique for the swept wing problem. But you will have, please understand, a bending equation, a torsion equation. That means you have two equations. Now two equations, you will have two errors, right? Now what do you do? What you have to do is, bending equation error, you apply the bending assumed function. Okay, that will give you a set of bending equations. Torsion equation will have its own error. You multiply by the assumed function for the torsion and that you write. Finally, you will have two sets of algebraic equations and which you solve. That is why you don't try to mix all the error everywhere. Please understand. Bending equation error multiplied by the bending assumed shape function. Torsion equation error multiplied by torsion assumed shape function.
Two values of Q.
Pardon?
We will have two values of, because we will have two sets of equation.
Yes.
Like this. So two values of Q.
You will not have, no, because you will have a bending deformation, torsion deformation. Two equations are there, right? What will happen is that will have some A1, A2, A3, B1, B2, B3. But these two are coupled equations. The equations are coupled. So you will find the bending deformation sitting in torsional equation, torsional deformation sitting in bending equation. So they will be a coupled equation and you will have a 2 by 2 or whatever, depending on the number of terms which you assume, you will get that form. That's why solving that problem is a little different from straight wing problem. Please understand. That is why when you apply Galerkin, understand thoroughly. You will have bending equation error, you will have torsion equation error. Multiply the bending equation error by the bending assumed. But you will find the constant. What is it finally landing up with? A1, A2, like that. What we have set here is, because this is only one equation, so this is set equal to 0. In that case, that will come as a matrix. Something into some A1, B1, something, etc. This is your external. But anyway, you are not bothered about this. You say the determinant of this going to 0 and you will get only one Q. One Q means you will have a Q square or quadratic equation, but finally you choose the lowest value for your divergence.